Food technology. In today's episode, we will take a look at refrigeration and freezing, pressure enthalpy and freezing methods, Part 2. Introduction. Pressure enthalpy diagrams are must to deal with calculations involved in refrigeration and various thermodynamic cycles. Therefore, these help in designing the refrigerators and related parts. Vapor compression cycle is presented on these charts, and property tables give accurate values of various thermodynamic properties of refrigerants and thereby facilitate the availability of data at various temperatures and pressure. In the present module, following topics are covered. 1. Molyneux's diagram or pressure enthalpy diagram. 2. Mathematical analysis of vapor compression refrigeration. 3. Superheating and subcooling. 4. Planck's equation. 5. Frozen storage. And 6. Methods of freezing. The following module will throw light on these diagrams and related concepts and numerical. 1. Pressure enthalpy diagram. The pressure enthalpy diagram or Molyneux's diagram, as described in Figure 1, it describes the various properties of a refrigerant under different conditions or phases. Using thermodynamic tables of refrigerants, the values are taken at both the saturation and superheated conditions for the refrigerant in question. On the pH diagram, pressure is indicated on the y-axis and enthalpy is indicated on the x-axis. Typically, enthalpy is in units of BTU by LB and pressure is in units of pounds per square inch or PSI. The upside-down U figure shown on the diagram designates the points at which the refrigerant changes phase. The left vertical curve indicates the saturated liquid curve and the right vertical curve indicates the saturated vapor curve. The region in between the two curves describes refrigerant states that contain a mixture of both liquid and vapor. The locations to the left of the saturated liquid curve indicate that the refrigerant is in liquid form, and locations to the right of the saturated vapor curve indicates that the refrigerant is in vapor form. The point at which the two curves meet is called the critical point. The importance of this point is that at any point above, no additional pressure will change the vapor into a liquid. The curves break up the diagram into three regions: 1. Liquid, 2. Vapor, and 3. Mix. 1. Liquid region. The liquid region is also known as the subcooled region. In this region, there are vertical temperature lines which increase as enthalpy is increased. Figure 8 is a simplified pH diagram illustrating the constant temperature lines. 2. Vapor region. The vapor region is also known as the superheated region. In this region, there are vertical temperature lines which increase as enthalpy is increased. There are also lines of constant entropy, which are also important. Entropy is the measure of the amount of disorder in the system. 3. Liquid-vapor mix region. In this region, the pH diagram shows horizontal temperature lines which indicate constant temperature. The mixed region is the phase change region where any addition of enthalpy will cause additional liquid to vaporize instead of raising the temperature. Figure 8 illustrates the horizontal temperature lines in the mixed region. There are upward sloping curves in the mixed region which indicate quality. Quality is a measure of the ratio of vapor mass to the total mass. For example, quality of 0.1 or 10%, which is located near the saturated liquid line, describes points that have 10% vapor by mass. Figure 2 represents a generalized Mollier diagram, and its various lines and regions are explained below. A. Line A to B represents the change from high to low pressure or expansion process. B. Line B to B represents the amount of liquid flashed off in the expansion valve cooling the remaining liquid. C. Line B to C represents the evaporation process at constant saturation temperature and pressure in the evaporator. At point C, the refrigerant is a dry saturated vapor. D. Line C to C represents the superheat absorbed by the dry saturated vapor. E. Line C to D represents the compression process. F. Line D to E represents the superheat given up by the vapor in the condenser. At point E, the refrigerant is a dry saturated vapor. G. Line E to F represents the condensation process at constant saturation temperature and pressure. At point F, the refrigerant is a saturated liquid. H. Line F to A represents the subcooling of the condensed liquid. 2. Mathematical analysis of vapor compression refrigeration. Refrigerating effect. Refrigerating effect is the amount of heat absorbed by the refrigerant in its travel through the evaporator. In Figure 3, this effect is represented by the expression Q EVAP equals, in brackets, H2 minus H1 Kj Kg. In addition to the latent heat of the vaporization, it may include any heat of superheat absorbed in the evaporator. Refrigeration capacity. The rate at which system will absorb heat from the refrigerated space or substance is known as refrigerating capacity. It is represented as QE equals M minus QE Kj bar S, where M equals mass flow rate of refrigerator through the evaporator and QE is refrigeration effect. Mass of refrigerant. Mass of refrigerant circulated, that is per second per ton of refrigeration, may be calculated by dividing the amount of heat by the refrigerating effect. Mass of refrigerant circulated is M equals 14,000 divided by 3,600 in brackets H2 minus H1 ton. Because 1 ton of refrigeration means cooling effect of 14,000 kJ bar H. Theoretical piston displacement. Theoretical piston displacement, that is per ton of refrigeration per minute, may be found by multiplying the mass of refrigerant to be circulated, which is again per ton of refrigeration per second, by the specific volume of the refrigerant gas, Vg in brackets 2, at its entrance of compressor. Thus, piston displacement equals 14,000 divided by 3,600 into, in brackets, H3 minus H2. Power theoretical required. Theoretical power per ton of refrigeration is the power theoretically required to compress the refrigerant. Here, volumetric and mechanical efficiencies are not taken into consideration. The power required may be calculated as follows. A. When compression is isentropic, work of compression equals H3 minus H2. Power required equals M into in brackets H3 minus H2, close the brackets, kW, where m equals mass of refrigerant circulated in kgs. B. When compression follows the general law PVN equals constant, work of compression equals N divided by N minus 1 into, in brackets, P3V3 minus P2V2, close the brackets, Nm bar kg. Power required equals M into N by N minus 1 in brackets P3V3 minus P2V2 into 1 by 10 to the power of 3 kW in brackets P in N bar M2. Heat rejected to compressor cooling water. If the compressor cylinders are jacketed, an appreciable amount of heat may be rejected to the cooling water during compression. If the suction and discharge compression conditions are known, this heat can be determined as follows. Heat rejected to compressor cooling water equals M into, in brackets, H3 minus H4, close the brackets, Kj bar S, where M equals mass of refrigerant circulated in kg bar S. 3. Superheating and subcooling. Superheating. Superheat is a measured value. It is the difference between two temperatures. Superheat is measured as the difference between the actual temperature of the refrigerant vapor and the saturation temperature of the refrigerant at that same point. As may be seen from the figure 4a, the effect of superheating is to increase the refrigerating effect, but this increase in refrigerating effect is at the cost of increase in the amount of work spent to attain the upper pressure limit. Since the increase in work is more as compared to increase in refrigerating effect, therefore, the overall effect of superheating is to give a low value of COP. Subcooling. Subcooling is the process of cooling the liquid refrigerant below the condensing temperature for a given pressure. In figure 4b, the process of subcooling is shown by 4 minus 4. As is evident from the figure, the effect of subcooling is to increase the refrigerating effect. Thus, subcooling results in increase of COP provided that no further energy has to be spent to obtain the extra cold coolant required. 4. Planck's equation. The freezing time is the time taken to lower the temperature of the product from its initial temperature to a given temperature at its thermal center. Planck's equation is an approximate analytical solution for a simplified phase change model. Planck assumed that the freezing process A commences with all of the food unfrozen but at its freezing temperature. B occurs sufficiently slowly for heat transfer in the frozen layer to take place under steady-state conditions. Planck's equation considers only phase change period during the freezing process. However, Planck's approximate solution is sufficient for many practical purposes. This method, when applied to calculate the time taken to freeze to the center of a slab, as shown in figure 5, whose length and breadth are large compared with the thickness, results in the following equation. Also, L1 equals mmL, that is for a food material, where mm equals moisture content of food, fraction. L equals latent heat of fusion of water, 333.2 kJ bar kg 0 degrees centigrade. The general form of Planck's equation is where P and R are constants accounting for the product shape with P equals 1 by 2, R equals 1 by 8 for infinite plate, P equals 1 by 4, R equals 1 bar 16 for infinite cylinder, and P equals 1 by 6 and R equals 1 by 24 for sphere or cube. The limitations of Planck's equation are as follows. 1. It neglects the time required to remove sensible heat above the initial freezing point. 2. It does not consider the gradual removal of latent heat over a range of temperatures during the freezing process. 3. Constant thermal conductivity assumed for frozen material. Despite these limitations, Planck's equation is the most popular method for predicting freezing time. 5. Frozen food storage. The storage life of fresh perishable foods such as meats, fish, vegetables and fruits can be extended by several days by storing them at temperatures just above freezing, usually between 1 to 4 degrees centigrade. The storage life of foods can be extended by several months by freezing and storing them at sub-freezing temperatures, usually between 18 and 35 degrees centigrade, depending on the particular food. Food, on being stored, may get spoiled by 3 mechanisms. 1. Living organisms may feed on the food and contaminate and spoil it. 2. Biochemical activity within the food itself with time diminishes its quality and usefulness. And 3. Physical processes, example, bursting and spillage of the contents of the package, may have the same effect. The rate of freezing has a major effect on the size of ice crystals and the quality, texture, and nutritional and sensory properties of many foods. During slow freezing, ice crystals can grow to a large size, whereas during fast freezing, a large number of ice crystals start forming at once and are much smaller in size. Large ice crystals are not desirable since they can puncture the walls and cells, causing a degradation of texture and the loss of natural juices during thawing. The freezing of foods involves 3 stages. 1. Cooling to the freezing point, that is, removing the sensible heat. Number 2 is freezing or removing the latent heat. 3. Further cooling to the desired sub-freezing temperature, that is, removing the sensible heat of the frozen food. Fresh fruits and vegetables are live products and thus they continue giving off heat that adds to the refrigeration load of the cold storage room. The storage life of fruits and vegetables can be extended greatly by removing the field heat and cooling as soon after harvesting as possible. The optimum storage temperature of most fruits and vegetables is about 0.5 to 1 degree centigrade above their freezing point. But this is not the case for some fruits and vegetables such as bananas and cucumbers that experience undesirable physiological changes when exposed to low but still above freezing temperatures, usually between 0 and 10 degrees centigrade. The resulting tissue damage is called the chilling injury and is characterized by internal discoloration, soft-scald skin blemishes, soggy breakdown, and failure to ripen. The severity of the chilling injury depends on both the temperature and the length of storage at that temperature. Lower the temperature, greater the damage in a given time. Therefore, products susceptible to chilling injury must be stored at higher temperatures. Chilling injury differs from freezing injury, which is caused by prolonged exposure of the fruits and vegetables to sub-freezing temperatures and thus the actual freezing at the affected areas. The freezing injury is characterized by rubbery texture, browning, bruising, and drying due to rapid moisture loss. The freezing points of fruits and vegetables do not differ by much, but their susceptibility to freezing injury differs greatly. Some vegetables are frozen and thawed several times with no significant damage, but others, such as tomatoes, suffer severe tissue injury and are ruined after one freezing. Products near the refrigerator coils or at the bottom layers of refrigerator cars and trucks are most susceptible to freezing injury. To avoid freezing injury, the rail cars or trucks should be heated during transportation in sub-freezing weather, and adequate air circulation must be provided in cold storage rooms. Damage also occurs during thawing if it is done too fast. It is recommended that thawing be done at 4 degrees centigrade. Number 6. Methods of freezing. The method of freezing is an important consideration in the freezing of foods. Common freezing methods include air blast freezing, where high velocity air at about 30 degrees centigrade is blown over the food products. Contact freezing, where packaged or unpackaged food is placed on or between cold metal plates and cooled by conduction. Immersion freezing, where food is immersed in low-temperature brine. Cryogenic freezing, where food is placed in a medium cooled by a cryogenic fluid such as liquid nitrogen or liquid or solid carbon dioxide, and the combinations of the methods above. In air blast freezers, refrigerated air serves as the heat transfer medium, and the heat transfer is primarily by convection. Perhaps the easiest method of freezing that comes to mind is to place the food items into a well-insulated cold storage room maintained at sub-freezing temperatures. Heat transfers in this case is by natural convection, which is a rather slow process. The resulting low rates of freezing cause the growth of large ice crystals in the food and allow plenty of time for the flavors of different foods to mix. This hurts the quality of the product, and thus this simple method of freezing is usually avoided. The next step is to use some large fans in the cold storage rooms to increase the convection heat transfer coefficient and thus the rate of freezing. These batch-type freezers, called stationary blast cells, are still being used for many food products but are being replaced by conveyor-type air blast freezers as appropriate, since they allow the automation of the product flow and reduce labor costs. A simple version of mechanized freezers called as straight belt freezer is very suitable for cooling fruits, vegetables, and uniform-sized products such as French fries. For smaller uniform-sized products such as peas and diced carrots, fluidized bed freezers suspend the food items by a stream of cold air, usually at -40 degrees centigrade, as they travel on a conveyor belt. The high level of air motion and the large surface area results in high rates of heat transfer and rapid freezing of the food products. The floor space requirements for belt freezers can be minimized by using multi-pass straight belt freezers or spiral belt freezers shown in, which now dominate the frozen food industry. In another type of air blast freezer called the impingement style freezer, cold air impinges upon the food product vertically from both sides of the conveyor belt at a high velocity, causing high heat transfer rates and very fast freezing. In contact freezers, food products are sandwiched between two cold metal plates and are cooled by conduction. The plates are cooled by circulating cold refrigerant through the channels in the plates. Contact freezers are fast and efficient, but their use is limited to flat foods no thicker than about 8 centimeters with good thermal conductivity, such as meat patties, fish fillets, and chopped leafy vegetables. In immersion freezing, food products are immersed in brine or another fluid with a low freezing point. At atmospheric pressure, liquid nitrogen boils at minus 195 degrees centigrade and absorbs 198 kJ by kg of heat during vaporization. Carbon dioxide is a solid at atmospheric pressure called dry ice and sublimes at minus 79 degrees centigrade while absorbing 572 kJ by kg of heat. The saturated nitrogen and carbon dioxide vapors can further be used to pre-cool the incoming food products before the vapors are purged into the atmosphere. The low boiling points and safety of these cryogenic substances make them very suitable for cryogenic freezing of food products. A common type of nitrogen freezer involves a long tunnel with a moving belt in it. Food products are frozen by nitrogen as they pass through the channel. Nitrogen provides extremely fast freezing because of the large temperature difference. Cryogenic cooling is used in limited applications because of its high cost. Sometimes cryogenic cooling is used in combination with air blast freezing for improved quality and reduced cost. The food product is first crust frozen in a bath of nitrogen to seal the moisture and flavor in, and then transferred into the air blast freezing section where the freezing process is completed at a lower cost. This practice also reduces to negligible levels the dehydration losses, which can be as high as 4% for poorly designed and maintained systems. Conclusion: refrigeration is the science of producing and maintaining temperatures below that of the surrounding atmosphere. Refrigeration could be achieved by melting a solid, sublimation of a solid, evaporation of a liquid. In a simple vapor compression cycle, compression, condensation, expansion, and vaporization are completed. To represent the steps thermodynamically relating to state of refrigeration, the pH chart is used. pH chart gives directly the changes in enthalpy and pressure during evaporation, compression, condensation, and expansion process for thermodynamic analysis, which is important to consider while designing refrigeration system. With this, we come to the end of today's episode. I hope you all had a good time learning. Thank you, viewers. Until next time, goodbye.